Have you ever stopped to consider that the vast, silent emptiness between the stars might not be quite as empty as we thought? What if something is passing through our neighborhood right now? Something that challenges every textbook notion we have about comets, space, and maybe even the very definition of natural. It feels like something fundamental has just shifted in the cosmos. After vanishing completely from our view, hiding tantalizingly behind the blinding glare of our own star, the object known as 3IATLAS has dramatically resurfaced. And honestly, the initial data pouring back from observatories across the globe is generating far more profound enigmas than definitive answers. The very first images snapped just as it reappeared, captured on Halloween night by the instruments at the Lowell Observatory, revealed something that by all established understanding of visiting interstellar bodies simply shouldn't be there. As Earth held its collective breath, anxiously anticipating any sign of this cosmic newcomer, telescopes situated at the Discovery Telescope in Arizona managed to lock onto a faint elusive smudge just beginning to ascend above the northeastern horizon. Following 8 full days of what astronomers call solar conjunction, a period where the comet was utterly obscured from our sight by the sun 3IATLAS, is officially back in view. But it's not the return itself that's snatching sleep from the eyes of researchers. It's the astonishing details they unearthed during their immediate analysis. The exterior shell of this celestial nomad is encased in material absolutely unprecedented in astronomical observation. A crust approximately 15 to 20 meters thick, composed entirely of organic compounds. Incredibly, these materials were not times formed within the comet's originating star system, but were instead forged over billions of years while it drifted aimlessly across the galaxy. Just let that sink in for a moment. Everything we are currently measuring, every spectral reading we are taking, might not be presenting the original pristine material from another solar neighborhood. Instead, we are observing an ancient shell that has been fundamentally resculpted by relentless cosmic radiation during an odyssey that likely began even before our own solar system coalesced into existence. Researchers spanning both Belgian and American institutions immediately ran these unexpected findings through rigorous computer simulations. The results they uncovered force a complete rewrite of our foundational comprehension of interstellar wanderers. Galactic cosmic rays, those high-energy particles hurled out by supernova explosions and colliding black holes, have been relentlessly pummeling this comet for an astonishing period, estimates ranging from 3 to 11 billion years. These intensely energetic particles managed to penetrate deeply into the surface layers, systematically dismantling complex molecules, subsequently fostering the creation of even more elaborate carbon chains, only to then break those new structures apart again. It's been operating as a continuous multi-eon cosmic forge. And here is precisely where the situation escalates beyond mere strangeness. The composition analysis yields data that simply does not correlate with any comet we have ever previously documented. Carbon dioxide is overwhelmingly dominant in the gaseous emissions observed at levels 7.6 times more abundant than the expected water content. The universal expectation is that comets are fundamentally dirty snowballs, primarily composed of water ice. This object barely qualifies for the definition. Furthermore, the spectral signature broadcasts the presence of elevated carbon monoxide levels and an unusually pronounced red reflection spectrum, indicative of the organic molecules heavily coating its exterior. But hold on, because there's even more data that refuses to fit neatly into established boxes. The measured ratio of nickel to iron found within the outgassing plume strikingly matches that of man-made industrial alloys, rather than the composition expected from naturally occurring cosmic dust. Even more perplexing, the ratio of nickel to cyanide is orders of magnitude higher than anything seen in any times known comet, including 2I, Borisov, our previous more conventional interstellar visitor. A few pioneering researchers are calculating the likelihood of these exact characteristics arising purely through natural cosmic mechanisms as being less than 1%. The polarization measurements, they are off the charts entirely. We are seeing extreme negative polarization, a phenomenon utterly unheard of in any comet observed up to this point. This isn't just a slight deviation. It's a statistically significant anomaly when compared against the entirety of the existing cometary data catalog. When sunlight reflects off the gas and dust surrounding 3IATLAS, it behaves in ways that conventional astrophysical models are completely incapable of explaining. Then we turn to its flight path. It's tracing a retrograde orbit moving opposite to the planets and is aligned within 5 degrees of the ecliptic plane. It seems to be threading its way through the solar system with an almost pre-planned precision. The statistical probability of such an alignment is estimated at merely 2%. Furthermore, it executed close flybys, passing within mere tens of millions of kilometers of Mars, Venus, and Jupiter, timing its perihelion passage perfectly for when Earth was positioned for minimum direct observation. The combined probability of these orbital coincidences lining up is a minuscule 0.005%. During the months of July and August, observers documented an event that seemed to actively defy basic physics. They recorded a sunward jet and anti-tail that pointed times directly toward times the Sunday. This is not an illusion caused by perspective like the familiar anti-tails seen on standard comets. This was an actual, tangible jet of material shooting in the direction of the source of heat and pressure. The scientific papers detailing these observations are published, the data validated, yet the underlying physical mechanism responsible remains completely elusive. As 3IATLAS swept closest to the Sun, reaching perihelion on October 29th, space-based solar observatories detected a rapid brightening far exceeding any known cometary activity. The object actually turned times bluer times than the Sun itself across certain wavelengths. Stop and consider that implication: a conglomerate of ice and rock momentarily outshining our star in specific parts of the spectrum. Satellites like Stereo SOHO and GOES-19 all recorded this identical astonishing phenomenon. Now here is a phenomenon that has theoretical physicists genuinely excited. The extremely close passage near the Sun created a flawless, naturally occurring laboratory setup for testing Einstein's general theory of relativity. Calculations regarding gravitational lensing predict that the Sun's immense gravity times should times bend the light emanating from 3IATLAS by exactly 27 arcseconds of angular separation. This is a measurable effect. However, the Atacama Large Millimeter, Submillimeter, Array ALMA detected the comet 4 arcseconds away from its predicted position near its closest approach. While some of that positional difference can certainly be attributed to gravitational lensing, there remains an unexplained residual, and that residual points toward an alternative explanation, one that is significantly harder for the scientific community to swallow: non-gravitational acceleration. This means the comet demonstrably changed its speed or direction without any apparent gravitational impetus. If this change were caused by jets of sublimating ice, pushing it like a natural rocket engine, the comet should have expended a minimum of 15% of its total mass. That translates to over 5 billion tons of gas and debris. A cloud of that magnitude should be physically impossible to overlook. Subsequent observations throughout November and December will either definitively confirm the existence of this gargantuan debris field or introduce a 10th major anomaly demanding explanation. Amateur astronomers situated throughout the northern hemisphere can now spot 3IATLAS using standard terrestrial telescopes. It appears as nothing more than a faint smudge above the eastern horizon during morning twilight, but that smudge is becoming increasingly discernible. As the object treks northward and gains angular distance from the Sun, the world's larger, more sensitive observatories are commencing their intensive observation campaigns. Crucially, the observational window for detailed spectroscopic analysis is now wide open. The hypothesis concerning the extensive organic crust resolves some of the existing riddles, yet simultaneously deepens others. If billions of years of galactic cosmic ray bombardment managed to process the surface down to a depth of 20 meters, this implies the comet has shed less than 1 meter of mass during the vast majority of its journey through our solar system. The intense solar heating experienced near perihelion times might times have sublimated a few dozen extra meters, but this is only plausible under very specific constraints regarding the comet's size. Regardless of the exact model, the takeaway remains: we are not examining primordial interstellar material. We are analyzing the highly processed residue of that journey. This realization forces an uncomfortable question upon us. How can we possibly ascertain the true origin of an interstellar object when its entire exterior surface has been so fundamentally altered? The spectral signatures, the gas emissions, the precise dust composition, all of it might convey much more information about the effects of sustained galactic radiation than about the comet's actual birthplace. It's akin to attempting to decipher the original text of an ancient book that has spent 3 billion years baking under relentless desert sun. The ink is still visible, but the text is no longer pristine. Some researchers are proactively advancing alternative interpretations. What if these myriad anomalies aren't isolated, disconnected events? What if they are all intricately linked by a single factor we have failed to incorporate into our current understanding? The alignment of its trajectory coming within 9 degrees of the direction historically associated with the famous WOW signal probably means nothing at all. It's likely just the statistical byproduct of optimizing a trajectory to facilitate planetary flybys while simultaneously ensuring maximum evasion of easy Earth-based observation. It's a statistical outlier, yes, but not mathematically impossible. The weird ratios of industrial metals, the bizarre polarization readings, the completely unprecedented surge in brightness, each one taken in isolation can be painstakingly explained away if one is determined enough to find a natural cause. But when you stack all 9 confirmed anomalies together, and potentially a 10th depending on upcoming reports, you exhaust the statistical margin for error. Nature is inherently peculiar, and the universe is immense enough for unlikely things to occur. But must times, all times, the unlikely things happen to the same time. Single object. The scientific community is currently focusing intense scrutiny on December 19th. This date marks 3IATLAS's closest approach to Earth. It won't be perilously close, but it will be near enough to offer observation opportunities that we may never see again for many decades, perhaps centuries. Every major telescope capable of acquiring a lock on the object will be collecting data simultaneously: advanced spectroscopy, precise photometry, polarimetry, and perhaps, if orbital geometry allows, even radar mapping. This is our definitive chance to capture the evidence required to move beyond speculation before the object recedes into the outer solar system indefinitely. The post-perihelion data is beginning to unveil details that the pre-perihelion observations simply couldn't capture. As the comet gains distance from the sun and begins to cool, volatile compounds locked deeper inside are sublimating and escaping. Every single gas molecule released acts as a tiny messenger, carrying crucial data about the interior composition, temperature profile, and overall structure. The spectrographs are working overtime, meticulously dissecting the reflected and emitted light into constituent wavelengths, actively searching for the molecular fingerprints of its constituent materials. Qicheng Zhang, an astronomer affiliated with Lowell Observatory, demonstrated something truly remarkable. Employing a relatively modest 6-inch amateur telescope, he managed to capture 3IATLAS when it was only 16 degrees away from the sun's disk, barely 5 degrees above the horizon. The comet was visible during that fleeting window of morning twilight, the narrow period when it clears the horizon, but before the sun has fully bleached the sky. If an instrument of that size can pull it out of the glare under those strained conditions, the resulting data harvest from the world's premier professional instruments is projected to be nothing short of extraordinary. The discovery of this thick, organic crust fundamentally reorients how we must interpret all times interstellar objects going forward. When galactic cosmic rays impact a mixture of ice and carbonaceous compounds, they initiate a profound cascade of chemical transformations. Carbon monoxide is oxidized into carbon dioxide. Water molecules are violently fractured through a process known as radiolysis. Complex organic molecules form, then subsequently break down only to recombine into entirely new configurations. It's an ongoing chemical evolution powered by the most high-energy particles available in the entire galaxy. Consider the larger implications. Every single interstellar visitor we detect in the future might be wearing an artificially imposed mask composed of radiation-processed surface material. The spectra we gather, the surfaces we analyze, they might be narrating the story of the object's journey through the galaxy rather than the story of its genesis. This is precisely like trying to deduce the original type of tree a piece of driftwood came from, after it has spent centuries being tumbled, eroded, and chemically altered in the open ocean. The original information is still buried there beneath the layers of transformation, but it's heavily obscured. Yet here is the central puzzle that keeps seasoned astronomers profoundly unsettled. The aggregate mathematics simply do not align for a purely natural origin when all observations are considered simultaneously. Take the orbital path as a starting point, a lone traveling retrograde, almost perfectly parallel to the main plane of the solar system, arriving at a specific moment in time when several planets are optimally positioned for flybys, all while Earth remains in a blind spot for direct optical observation. Input those parameters into any orbital mechanics simulator and watch the calculated probability plummet into the realm of statistical insignificance. Now layer on the compositional anomalies, those industrial-grade nickel ratios, the astonishingly low water content for something called a comet, and the extreme polarization that shatters all known dust interaction models. Each individual data point strains credibility when viewed alone. When you stack them, you are either witnessing the cosmic equivalent of winning the universe's largest lottery 9 successive times, or perhaps something fundamentally different is operating here. The radiation processing theory admirably accounts for the thick organic shell, the abundance of carbon dioxide, and the resultant red spectral tint. However, it completely fails to explain the significant nickel enrichment. It offers no mechanism for the precise trajectory. It cannot account for the dynamics causing the observed anti-tail. And it certainly offers no framework for the object suddenly achieving brightness levels far beyond established limits, coupled with that dramatic blue hue near perihelion. Solar monitoring observatories recorded critical telemetry during those precise hours when 3IATLAS was nearest the sunday. The recorded light curve spiked with an intensity and rapidity that outpaces every known comet in the historical record, not just a little unusual, but entirely outside the standard statistical distribution. That distinct color shift to blue strongly suggests an energy release or conversion mechanism occurring within the material that standard sublimation models cannot predict. Energy, after all, cannot simply materialize. If 3IATLAS suddenly became intensely brighter and bluer, it signifies that stored energy was being unleashed or that incoming solar energy was being converted into different forms of radiation. Conventional explanations would involve the sudden uncovering of fresh, highly volatile ice or perhaps a catastrophic internal breakup. Both scenarios are expected to generate observable plumes of debris and an extended irregular coma. The observational checks planned for November will confirm whether that expected debris cloud actually exists. The composition of the organic crust itself poses another structural conundrum. We have a crust 15 to 20 meters thick, composed of carbon-rich compounds that have been bombarded by cosmic rays for billions of years. This isn't a superficial film, it's a substantial protective shell. How then does sublimation occur effectively through such a robust barrier? The standard model dictates that solar heating creates pressure which fractures the surface, allowing trapped gases to escape. But this mechanism should continually expose fresh, unprocessed interior material. The fact that we are still times observing processed organics suggests either that the crust is somehow regenerating itself or that the fundamental process of gas release is entirely different from our current understanding. Consider the thermal implications. Organic compounds are notorious for being excellent thermal insulators. A 20-meter thick crust should effectively block the vast majority of solar heating from reaching the interior water ice. Yet 3IATLAS exhibits very vigorous outgassing activity. This means either the crust is permeated with fissures and cracks, allowing thermal penetration, or energy is reaching the core via non-radiative pathways. Every single potential explanation generates vastly different testable predictions about what we should observe next. The perplexing antitail phenomenon observed back in July and August remains fundamentally unexplained. Standard jets of gas and dust are reliably pushed times away, times from the sun by the combined forces of radiation pressure and the solar wind. A jet directed times toward times, the sun requires either dust particles possessing highly unusual electromagnetic properties that cause them to fall toward the sun faster than radiation, pressure pushes them away, or alternatively, some form of active directed propulsion emanating from venting on the sunward side. Neither explanation fully accounts for the observed geometry of the jet. Several dedicated research teams are now cautiously exploring the possibility of significant subsurface activity. If the comet's interior harbors pockets of superheated compressed volatile ices, sudden failure of a subterranean reservoir could generate powerful jets firing in any direction irrespective of the immediate solar input. This mechanism mirrors terrestrial geysers or the impressive nitrogen plumes observed on Pluto. While such internal pressure release could certainly explain the directional jets, it necessitates a specific layered internal structure and composition that we haven't confirmed. The polarization data continues to be particularly troublesome for models adhering strictly to established cometary physics. Light scattering off dust particles invariably produces predictable polarization patterns dictated by the particle size, shape, and chemical makeup. The extreme negative polarization emanating from 3IATLAS suggests dust particles possessing inherent characteristics unlike anything else previously documented. Either the massive radiation processing has created uniquely structured, perhaps crystalline particles, or the dust simply isn't composed of the expected silicate and carbon grains. Laboratory experiments are now racing to replicate these conditions. Scientists are subjecting various mixtures of ice and organic compounds to simulated multi-billion-year cosmic ray bombardment, followed by rigorous analysis of the resulting material. If they can successfully synthesize dust exhibiting the same polarization signatures, it would provide strong validation for the natural processing hypothesis. If they fail, we will be compelled to seek entirely new explanations for the composition of this comet's coating. The elevated nickel enrichment continues to baffle geochemists. While natural cosmic dust naturally incorporates nickel, the typical ratio relative to iron usually mirrors the overall solar system average abundance. Industrial alloys, conversely, are engineered with specific nickel to iron ratios precisely optimized for achieving superior strength and resistance to corrosion. The fact that the emissions from 3IATLAS display ratios matching these engineered specifications rather than expected natural abundances registers as statistically bizarre. Again, not impossible. Perhaps a specific type of supernova remnant could create such skewed elemental zones, but it certainly demands highly unusual formative conditions. Could material ejected from a very specific layer of an exploding star possess these non-standard elemental ratios? Absolutely. If 3IATLAS originated from such unique supernova ejecta rather than a standard slowly cooled protostellar disk that could account for the chemistry, this is thankfully testable. Other elements should show corresponding deviations if this supernova fragment theory holds true. The crucial close approach on December 19th promises to deliver the highest resolution data acquired to date. At a distance of approximately 0.4 astronomical units, it will be near enough for radar mapping contingent on the precise geometry aligning correctly. Radar waves can penetrate the surrounding dust and gas cloud to generate actual three-dimensional maps of the nucleus's shape, size, and surface topography. Radar can also measure the object's rotation rate and reveal subtle variations in surface features. Most importantly, it measures radar reflectivity, which is a direct indicator of internal structure and material density. If 3IATLAS is a genuinely natural comet, even one as strange as this, the radar signature should display an irregular, lumpy shape with heterogeneous surface properties, the expected result of accretion and subsequent space, weathering. If, however, the radar reveals something geometrically uniform or unexpectedly regular, that data point alone will carry immense significance. Ground-based observatories are coordinating spectroscopic campaigns designed to run across multiple nights. The goal is to observe how the emission lines shift and change over time. They will monitor the production rates of various molecules and look for correlations linking gas release to the comet's distance from the Sun or its rotational phase. The objective is to build a fully integrated dynamic picture of the comet's ongoing activity cycle. The data derived from these synchronized campaigns will bridge critical informational gaps and rigorously test the currently competing physical models. The orbiting ultraviolet observatories are proving particularly indispensable. The specific Lyman alpha emission signature derived from hydrogen atoms surrounding comets serves as an excellent tracer for water dissociation. If 3IATLAS truly harbors as little water as the initial analyses suggest, the surrounding hydrogen cloud must be dramatically smaller than those associated with typical comets. Confirming this low hydrogen output would definitively validate the compositional anomaly and definitively rule out any observational artifacts causing the low water readings. One hypothesis that consistently reappears in confidential electronic communications, though rarely spoken aloud in public forums, is that we might be analyzing a fragment rather than a pristine, intact primordial object. What if 3IATLAS was once merely a piece of a much larger body that shattered during its journey? The colossal organic crust would have formed on that original larger parent body, and the fragment would have simply inherited it. The peculiar bulk composition could then be explained by exposing interior materials through the catastrophic breakup event. This concept offers a compelling middle ground explanation, accounting for several anomalies, while remaining entirely within the realm of known natural processes. However, fragmentation events virtually always leave evidence lingering debris, trails, companion fragments, or highly irregular shapes resulting from the trauma of separation. So far, detailed observations have failed to reveal any obvious indicators of recent fragmentation. The light curve has maintained a stable progression without the sudden chaotic variations expected from an unstable or segmenting object. Of course, if the breakup occurred millions of years ago while the object was traversing interstellar space, any smaller fragments are now impossibly dispersed and undetectable. The issue of the object's sheer age is itself a fascinating subject. If 3IATLAS has genuinely spent 3 to 11 billion years adrift between stellar nurseries, it predates the formation of most of the planets within our own solar system. It was already ancient by the time Earth began to cool and stabilize. The organic molecules currently coating its surface are demonstrably older than the earliest known origins of life on our world. We are, in essence, analyzing chemical compositions that existed before biology, before planetary conditions recognizable to us even existed. What was the Milky Way galaxy like when this object initiated its long journey? The galactic structure was different. The stellar populations were younger. The overall chemical abundances were altered. Star formation rates were significantly higher, and the frequency of supernova events was distinct. The interstellar medium itself possessed different physical properties. If 3IATLAS coalesced during that remote era and retains chemical signatures reflecting those conditions, it represents a direct physical sample of ancient galactic history. But here lies a significant contradiction in that narrative. Any object tumbling through the vastness of interstellar space for billions of years should accumulate a substantial bombardment history from micrometeoroids and high-velocity dust grains. Every single one of those impacts erodes the surface, generates micrometeorite craters, and alters the chemical makeup of the outer layers. While the sustained radiation processing might smooth over some of these features, it shouldn't erase all evidence of ancient collisions. Detailed radar scans or high-resolution imaging should logically reveal impact scars if this object is truly billions of years old. The object's rotation rate will also yield vital clues. Natural bodies that have tumbled chaotically through the interstellar void for eons should exhibit complex rotational states resulting from billions of accumulated gravitational and physical torques from impacts. By monitoring the light curve over a sufficiently long duration, astronomers can determine if the object is tumbling chaotically or rotating smoothly around a single axis. A simple, stable rotation might suggest a much more recent formation event or a recent stabilization impact. Complex multi-axis tumbling would align much better with the narrative of an ancient lonely wanderer. There is one final highly sensitive aspect of this entire scenario that, while rarely uttered in formal reports, dominates private discussions: the current detection rate of interstellar objects. We found Oumuamua in 2017, followed by Borisov in 2019, and now 3IATLAS in 2025. That's 3 confirmed objects discovered within a span of just 8 years. Statistical models based on our current sky survey capabilities predicted we should find maybe times 1 times such object per decade. We are currently observing an arrival rate triple the established expectation. This means one of 3 things: either the galaxy harbors vastly more interstellar wanderers than our population models accounted for, or we are experiencing an astronomically improbable run of good luck in our random discoveries. Or the most unsettling possibility: something about these recent detections suggests they are times, not times, random events. The first possibility demands a complete overhaul of galactic population models. The second is statistically permissible, but becomes increasingly improbable with every new confirmation. The third possibility leads us down paths of speculative inquiry concerning selection effects or perhaps intentional targeting. Consider this hypothetical framework. If an advanced technological civilization sought to conduct a systematic survey of star systems, deploying physical probes would be the most efficient method. Such probes would by necessity have to be engineered to survive multi-millennial interstellar transit, meaning robust structural integrity and substantial radiation shielding. They would require onboard propulsion systems capable of making necessary course adjustments, which would manifest as the non-gravitational accelerations we observe. They would logically optimize their trajectories to use planetary flybys to maximize data collection efficiency. And perhaps most importantly, they would likely arrive at their target systems during periods when detection is inherently difficult, thereby minimizing immediate attention. Now review our 3 interstellar guests through this speculative lens. Oumuamua, tumbling, elongated, exhibiting an acceleration that defied conventional comet-based explanations. Borisov, seemingly more conventional, perhaps a control sample or a baseline comparison object. And then there is 3IATLAS, combining a maximum number of extreme anomalies with a trajectory timed for optimal evasion of easy detection. Each visitor seems to offer a different lesson regarding the possibilities of interstellar transit. This is where the academic conversation becomes risky for professional longevity. Suggesting the possibility of an artificial origin invites immediate, intense scrutiny and often professional dismissal. The evidence, as scientists are careful to state, does not offer definitive proof of artificiality. So why introduce such speculation? However, conversely, the data also fails to offer definitive proof of natural origin either. At some juncture, when the sheer number of accumulating anomalies becomes statistically overwhelming, refusing to at least entertain alternative hypotheses begins to look less like scientific rigor and more like intellectual stubbornness. The scientific community maintains established protocols for handling such sensitive subjects. One must rigorously present all known natural explanations first. One must emphasize the existing uncertainties in the measurements. One must rely heavily on phrasing such as requires further deep investigation and remains unexplained by current models. one must emphatically avoid leaping toward exotic conclusions. Yet behind the careful, measured language, there is a pervasive, undeniable awareness that something genuinely unprecedented is unfolding. Public communication regarding 3IATLAS presents its own set of challenges. How does one responsibly convey the immense significance of these findings without inducing widespread panic or generating unrealistic expectations? Let's be clear, the object poses no physical threat to Earth. It is not on a collision course, and crucially, it has not been definitively proven to be artificial. But at times is displaying multiple interlocking behaviors that severely strain the limits of our established cometary physics. Striking the appropriate balance between radical transparency and public responsibility is extraordinarily difficult. Some established researchers argue for a pure data release present every single observation, publish every measurement, release the statistical analysis, and trust the global public to grasp the necessary nuance and inherent uncertainty. Others fear that incomplete information will inevitably be cherry-picked, leading to sensationalized, unfounded conclusions, drowning out careful scientific discourse. Media coverage has already reflected this dichotomy, swinging wildly from sober coverage of the radiation crust discovery to breathless headlines featuring the alien spacecraft angle. Scientists caught in the crossfire struggle to issue necessary corrections while simultaneously acknowledging the legitimate, profound mysteries that remain. Meanwhile, the relentless observation campaigns continue. Every single night that weather conditions permit, telescopes worldwide are tracking this stellar wanderer. Every new spectrum captured adds layers to the data pool. Every refinement of its position measurement tightens the constraints on its orbit. Every detection made in a novel wavelength restricts the potential physical models. The dataset now accumulating for 3IATLAS is growing exponentially faster than what we possessed for Oumuamua or even Borisov. Whatever this object ultimately proves to be, we are studying it with a depth of scrutiny never before applied to an interstellar visitor. The observations scheduled throughout November are especially critical. This specific period offers the ideal convergence. The object is distant enough from the Sun for excellent visibility conditions, yet remains sufficiently close to Earth to yield strong signal returns. Local atmospheric conditions are also paramount. Clear, steady nights produce the sharpest spectra. Atmospheric turbulence blurs images and introduces measurable noise. Observatories situated at high altitudes with stable seeing conditions are being prioritized for the most detailed characterization measurements. International coordination is absolutely mandatory for success. While the comet is primarily visible from the northern hemisphere, different longitudinal positions ensure that as one observatory's window closes, another's opens, allowing for nearly continuous 24-hour monitoring. Coordinating these global efforts involves complex scheduling logistics and establishing secure, high-bandwidth data-sharing agreements across national boundaries. The payoff, however, is comprehensive round-the-clock surveillance. The contribution of the amateur astronomy community is also proving invaluable. A widely distributed synchronized network of small telescopes can provide a temporal coverage density that no single monolithic professional facility can possibly replicate. While they cannot match the resolving power or sensitivity of the major instruments, they excel at tracking subtle changes in brightness, detecting sudden outbursts, and providing crucial early alerts for professional telescopes to swivel toward for targeted follow-up. This truly represents citizen science operating at its absolute zenith, professionals and amateurs collaborating seamlessly. The December 19th close approach is currently being planned with the strategic rigor usually reserved for complex expeditions. Specific target acquisition windows are being meticulously calculated. Instrument configurations are being optimized for peak performance. Observation schedules are drafted, debated, and frequently revised. Contingency plans account for everything from unexpected weather disruptions to technical hardware failures and unforeseen astronomical developments. This event represents humanity's single best opportunity to truly comprehend 3IATLAS before it vanishes from the inner solar system forever. After December, the comet will continue its outbound trajectory. By the middle of 2026, it will have already sailed past the orbit of Jupiter, fading beyond the reach of all but the most powerful telescopes. Eventually, it will disappear back into the profound interstellar void, taking whatever definitive secrets it holds along with it. Whether we manage to solve the core mysteries by that time, or whether we simply amass a larger collection of profound questions, remains to be determined. The enduring legacy of 3IATLAS is already secured, regardless of its final classification. It is forcing the entire field of astrophysics to confront long-held assumptions regarding interstellar objects, the expected physics of cometary behavior, and the true limits of natural phenomena. The discovery of the radiation-processed, organic crust alone will fundamentally reshape how we interpret every future interstellar visitor we detect. The unusual orbital statistics will directly influence how we structure our future detection search strategies. The compositional oddities will serve as concrete targets for forthcoming laboratory simulations. And then there is that persistent, non-zero possibility, however slim, that we are in fact observing the first confirmed technological artifact from an intelligence originating beyond our solar system. If that suspicion proves true, if the anomalies are not attributable to statistical noise, observational errors, or exotic natural physics, but are instead the deliberate signatures of purpose and design, then everything changes in the human story. Imagine the implications. It would confirm definitively that we are not isolated in this galaxy. It would provide tangible proof that interstellar transit is physically viable. It would offer evidence that other civilizations exist, are operational, and are actively engaged in exploring the cosmos. The philosophical ramifications alone would be staggering. Global religions would immediately need to reconcile their doctrines with the reality of non-human intelligence. Governments would have to instantaneously reprioritize cosmic security and exploration budgets. The focus of pure science would pivot toward reverse engineering the nature and intent of these visitors. But we have not reached that conclusive point yet. The data remains genuinely ambiguous. Plausible natural explanations, while increasingly convoluted and demanding, still exist within the scientific framework. Extraordinary claims require and must be supported by extraordinary evidence. While the evidence we have is certainly unusual, it has not yet reached that absolute threshold. The path forward demands more sophisticated observation, deeper analysis, and the rigorous testing of every conceivable alternative hypothesis. What we can assert with absolute certainty today is that 3IATLAS has permanently carved its name into scientific history. It is the third confirmed interstellar body. It is the most intensely scrutinized visitor from another star system ever encountered. It has served as the catalyst for entirely new discoveries regarding galactic chemistry and the effects of cosmic radiation. It has instigated essential debates concerning the very methodology of science and the appropriate ways to search for extraterrestrial intelligence. And it remains an object of profound fascination for hundreds of millions of people watching from the comfort of their home planet. The narrative is far from concluded. The observations slated for November and December will certainly add pivotal chapters. The subsequent analysis of that data will continue well into 2026 and likely beyond. New papers will be published, scrutinized, debated, and possibly retracted. Models will be tested, relentlessly refined, or ultimately discarded. The scientific process is inherently incremental, accumulating verifiable knowledge, even when definitive conclusions remain tantalizingly out of reach. For the immediate future, 3IATLAS is traversing our solar system, a true traveler from distant gulfs carrying mysteries we are only just beginning to decode. Every single photon it reflects contributes a piece to the narrative. Every molecule it releases adds another phrase to the story. Every successful measurement brings us measurably closer to whatever the ultimate truth might be, regardless of what that truth entails. And so we continue to watch, to measure, to hypothesize, and to wait for the revelations that the December observations promise. The human reaction to 3IATLAS itself offers a powerful reflection of our own species. When confronted with true, unadulterated cosmic mystery, we react with predictable patterns. Some individuals embrace the open-ended uncertainty, finding intellectual beauty in the unresolved questions. Others fiercely demand immediate, concrete explanations, exhibiting profound discomfort with ambiguity. Scientists, by professional necessity, occupy a difficult middle ground, obligated to maintain rigorous skepticism while simultaneously being personally drawn toward the most extraordinary possibilities. The reaction on social media following the initial anomaly reports was immediate and explosive. Trending hashtags, viral memes, and countless amateur analysts poured over every single publicly released image, trying to spot some telltale detail that the professional astronomical community might have overlooked. The democratization of scientific data means that everyone can now participate in the discovery process. For better or worse, this crowdsourced analysis has on rare occasions helped flag legitimate findings, but it also generates a relentless torrent of false alarms. The psychological weight of a potential first contact event, even an indirect one, involving an unmanned artifact, cannot be overstated. Surveys consistently indicate that the majority of people times believe times intelligent life exists elsewhere, but that abstract belief is vastly different from encountering concrete confirmation. Actually finding evidence instantly transforms abstract philosophy into tangible reality, forcing humanity to confront its precise place within the vastness of the cosmos. Religious institutions are already actively developing interpretive frameworks. While some existing theological systems readily incorporate the concept of extraterrestrial intelligence, others will require significant reevaluation of foundational texts and doctrines. The universe is demonstrably larger and far stranger than ancient prophets could have conceived. Governmental and defense agencies are also observing these developments with extreme vigilance, though public statements are scarce. Space agencies operate under strict protocols for handling unexpected off-world discoveries. Military organizations track every object approaching Earth's vicinity, regardless of whether it is deemed natural or otherwise. Intelligence services are closely monitoring for any indication of technological signatures. Should 3IATLAS ever be confirmed as artificial, the geopolitical consequences would be immediate and transformative. Who speaks for Earth? Who determines the parameters of any potential response? Who controls the dissemination of this paradigm-shifting information? These questions have theoretical answers codified in international agreements and UN mandates, but theory often fails spectacularly when faced with the sudden pressure of reality. When communication decisions must be made in mere seconds, when media cycles demand instantaneous reactions, and when public pressure for full transparency mounts, those carefully drafted protocols might easily collapse under strain. Science fiction has poorly prepared us for actual contact. Those narratives typically feature dramatic encounters, clear intent, and easily decipherable communication. The likely reality of 3IATLAS, if artificial, is one of deep ambiguity, an object merely passing through, showing no inclination to slow down or engage, leaving behind only indirect data and statistical puzzles for us to try and solve. No grand cosmic greeting, just an accumulation of increasingly difficult questions. Perhaps this quiet approach is the intent. An advanced civilization conducting a long-term galactic survey would logically prioritize minimal interference with the societies they are observing. Collect the data, perhaps leave a marker, and move on? The prime directive trope from fiction was speculation, certainly, but it reflected a rational consideration of how responsible, non-disruptive exploration might proceed. If 3IATLAS is indeed a probe, its remote operators might currently be monitoring our global response to this ambiguity. Or perhaps we are simply pattern-seeking primates, as humans are evolutionarily programmed to be identifying meaningful shapes within random noise. Humans possess an exceptional capacity for pattern recognition, even when no true pattern exists. This was a vital survival trait For our ancestors, better to assume a non-existent predator is present than to miss one that truly is. But this same mechanism fuels conspiracy theories, creates false correlations, and leads us to perceive intelligence where only blind nature is at work. The scientific methodology itself exists largely as a necessary countermeasure to our inherent pattern-seeking bias, demanding reproducibility testing, competing hypotheses, and strictly quantifying all uncertainties. This framework protects us from self-deception, yet it also creates immense tension when genuinely extraordinary phenomena appear. What threshold of evidence is truly sufficient? When does justified scientific skepticism begin to resemble willful denial? Different experts possess different internal thresholds for confirmation. Some view the convergence of anomalies in 3IATLAS and conclude we have crossed into a domain requiring entirely new physical explanations. Others see the identical data and conclude we simply require superior natural models and more patience before resorting to exotic interpretations. Both positions are rationally defensible, both stem from highly qualified individuals analyzing the same empirical facts. This intellectual friction is actually healthy for the scientific enterprise. Consensus arises from rigorous debate, not from immediate uniform agreement. The current disagreement over 3IATLAS reflects genuine scientific uncertainty, not a failure of method. We are scientifically supposed times to argue vigorously over ambiguous data that is the engine of knowledge advancement. The media's tendency to frame scientific debates as a zero-sum game where one side must be absolutely correct and the other definitively wrong often obscures the messy reality. The truth frequently incorporates elements from several competing models. 3IATLAS might, for instance, be a natural comet formed under highly unusual conditions that explains times, sometimes anomalies, while other anomalies might stem from observational biases we haven't fully isolated yet. Or it could be something entirely outside our current theoretical grasp. The public's grasp of scientific uncertainty remains complex. People strongly desire definitive black and white answers. Scientists, however, deliver data packaged in probabilities and confidence intervals. This disconnect inevitably breeds frustration on both sides. Researchers feel misrepresented when careful caveats are excised in favor of punchy headlines, while the public can feel misled when scientific consensus evolves as new data emerges. Building enduring trust requires better, clearer communication flowing in both directions. Educational outreach surrounding 3IATLAS has been remarkably extensive. Astronomers are hosting public viewing sessions, museums are creating specialized exhibits, planetariums are running novel programs, and digital platforms are overflowing with explanatory content. The aim is to foster comprehension, not just of what times we see, but how science observes, analyzes, and ultimately formulates conclusions. Scientific literacy in this context arguably matters more than the discovery itself. The subtle economic repercussions are also beginning to manifest. Private aerospace entities are monitoring the situation with acute interest. If interstellar objects prove to be far more common than previously modeled, or if artificial visitors become a confirmed possibility, it immediately changes the business calculus for space exploration. Detection networks suddenly gain immense strategic value. The feasibility of future intercept missions shifts from theoretical conjecture to strategic planning. The entire framework for space commercialization is subject to immediate reevaluation based on assumptions about what occupies the void between the stars. Academic funding cycles are already reacting. Grant proposals that specifically mention interstellar objects are receiving elevated priority review. Universities are creating new dedicated research positions. Instruments originally designed for mapping exoplanets are being rapidly repurposed to maximize their effectiveness in detecting these transient visitors. The field is expanding, rapidly driven by the realization that encountering visiting objects with some regularity might no longer be improbable. If we detected 3 in 8 years, it strongly implies that more are certainly en route. This projection, of course, rests on the assumption of purely random arrival vectors. If the detection rate is demonstrably non-random, if there is clustering or evidence suggesting intentional navigational choices, then the entire statistical foundation of our current search protocols dissolves. We would then be dealing with an entirely different cosmic reality. The search for extraterrestrial intelligence, SETI, has traditionally concentrated its efforts on passively listening for radio transmissions. The underlying assumption was that radio waves are a universal means of communication, that civilizations either broadcast intentionally or leak technological noise, and that we would be positioned to intercept those signals. However, physical probes offer distinct advantages. They can carry exponentially more information than any broadcast signal. They can perform high-fidelity local observations. They possess the potential for physical interaction with the environment they investigate. If a civilization is genuinely serious about comprehensive exploration, sending hardware makes the most logical sense. The Voyager probes carried physical golden records. For precisely this reason, we understood the permanence and richness of a physical message. An advanced civilization would likely reach the same conclusion, deploy probes to targets of interest, gather detailed local intelligence, and perhaps leave behind markers of their passage. Over the course of millions of years, a single technologically mature civilization could potentially survey a substantial fraction of the Milky Way. This remains speculation, of course. We have no data on the longevity of technological civilizations. We don't know if interstellar travel is practical, even for beings far more advanced than us. The Drake equation remains choked by too many unknown variables. However, the arrival of 3 interstellar visitors in less than a decade, with one exhibiting such a host of profound anomalies, shifts the probabilistic landscape significantly. Fermi's paradox asks, if intelligent life is common and interstellar travel is achievable, where is everybody? The silence has historically been absolute, but perhaps our search methodology has been fundamentally flawed. Maybe the evidence isn't found in radiostatic, but in physical artifacts, traversing our solar system distinguishable from natural bodies only through painstaking statistical analysis across multiple disparate data parameters. The philosophical queries spiral outward from this point. If intelligence is statistically common, why the variety in observed approaches Borisov appeared perfectly natural? Oumuamua showed intriguing hints of non-natural mechanics. 3IATLAS displays extreme multifaceted anomalies. Are these signals from different civilizations employing different technologies? Are they varied missions from the same source? Or is it a confusing mix of natural objects interspersed with 1 or 2 artificial visitors? We will not resolve these meta-questions in November or December. We may not resolve them in our lifetimes. But every single observation narrows the field of possibilities. Every analysis refines our current incomplete understanding. This process, frustrating, exciting, gradual, and deeply human, is precisely what discovery entails. We are engaging in the fundamental human act, observing the unknown, and striving through method and collaboration to construct a coherent narrative from it. The generation of children who are currently watching this unfolding story will inherit a universe perceived as vastly different from the one their parents knew. Whether 3IATLAS ultimately proves to be a stunning example of extreme natural physics or the first confirmed evidence of visitation, the awareness has irrevocably shifted. We are not alone in the sense that our system is routinely visited by objects originating elsewhere. The galaxy is clearly a dynamic, chemically interconnected, and physically accessible domain. This realization has significant implications for humanity's long-term strategy. Proponents of intensive space exploration argue that confining our species to a single planetary cradle represents an unacceptable existential risk. The evidence that interstellar objects are regular visitors and that some might even be engineered artifacts powerfully reinforces the need for developing independent off-world capabilities. This imperative stems not from competition or fear, but from the recognition that exploring the void is what technologically mature species eventually do. The engineering hurdles remain monumental. Reaching even the nearest stars requires propulsion breakthroughs beyond our current theoretical reach. Surviving the transit across interstellar vacuum demands material science solutions we have yet to conceive. Yet watching 3IATLAS successfully complete that immense journey proves its physical possibility. Something either natural mechanism or designed artifact managed the transit. What nature or others have achieved it is the eventual destiny of humanity to also attempt. That might be the profoundest legacy of 3IATLAS, definitive proof that interstellar space is in fact crossable. It is a demonstration that our solar system is not an isolated sanctuary, but a waypoint regularly utilized by objects arriving from distant stellar depths. It serves as profound inspiration to imagine humanity's own future among the stars, reminding us that the universe is vastly richer, stranger, and more surprising than we typically allow ourselves to believe. December 19th is approaching quickly. The great telescopes are being prepped. The observer schedules are locked in. The entire world is watching, suspended between possibility and probability. Whatever data emerges from that critical period, whatever subsequent analysis is performed, and whatever cautious conclusions eventually settle into the textbooks, this moment matters. We are currently witnessing an astronomical event that is both rare and potentially singular, an object from another star system, exhibiting behaviors that strain our current explanatory power, offering mysteries. We are only beginning to catalogue. Right now, the questions vastly outnumber the certainties. The unknowns dwarf the known. And this perhaps is precisely how discovery must always function. Comfortable certainty signals the end of learning. Uncomfortable ambiguity signals that we have reached the absolute frontier, pushing forward into territory no human mind has previously mapped. 3IATLAS has brought us forcefully to that frontier. Where humanity proceeds from this point depends entirely on what we manage to uncover next, and whether we possess the courage to follow the evidence wherever scientifically it leads. If you find this content interesting, please like and leave a comment. This video from Cosmic Warning A to Z, thank you for watching.